Okay, so we're going to talk about inductors today, or in this lesson. And there's a video marked there that I would like for you to watch, which is a good introduction into inductors. Okay. So inductors, they have when you have a change in current, it will produce a voltage across itself. So if you can think of a device, it will produce a voltage across itself or in a nearby circuit by a changing magnetic field. So we talked about magnetic fields, now we are talking about changing the magnetic fields, or what happens when you have a current that changes, that it will produce a magnetic field. So an inductor is a particular device that has a specific measurement of inductance. So in this case, we have a current that is increasing. You see the current is increasing right here. So it starts off at 0 and then it goes up like that. So when that happens, this T1 here, then you have a magnetic field which is developing like that. A magnetic field which is developing. As the current increases, that magnetic field starts getting greater, like this. And when the current starts decreasing, like this, see the current is decreasing right there, then that magnetic field collapses on itself, like this. So you have a constant magnetic field that is developing and collapsing as this waveform goes to this peak, goes to 0, goes down, comes back up. Okay. And that's the basis of inductance. So that's the two waveforms. And Faraday was a scientist who came up with the laws of induction. And what he said was that you have to have a particular motion between the wire and the magnetic field to induce a voltage across that wire. I'll show you as we go along in how that happens. The other one, the second law he came up with was how much of a voltage is being produced. And that depends on the rate of change of the magnetic flux that the wire will encounter. And this is the rule which says how much voltage is induced on a wire. And this is the formula for calculating the induced voltage. So V sub L is the instant voltage, so right here. This is the inductance, so like we were talking about resistors, we use the letter R. So inductors, the letter L. And this is the change in di and dt. So when we were talking about DC, we never talked about a phase relationship, but with AC or with inductors, there is a phase relationship. So we are talking about inductors in this case, but the other device, the next device we are going to be talking about is capacitors. They also have a thing called a phase relationship where the voltage and the current don't follow each other. So with like a resistor, the current and the voltage, they followed each other. There was no difference in the two. But in capacitors and inductors, it does not work like that. And the difference between the peaks is a phase relationship. And it's less than or equal to 90 degrees, the phase relationship. Lenz's law, which says that the induced voltage will always oppose its source. Okay? So kind of keep that in mind, that we're talking about opposition. The other device we've talked about so far, which has opposition, is a resistor. Inductors also have a kind of resistance, but it's slightly different as compared to a resistor. And the reason why that is with resistors, the voltage and current are in phase with each other. With inductors, they're not. So if you increase the current, then the magnetic field will expand, when we saw that in the previous slide. And when you have this increase of the magnetic fields, it produces a voltage in the coil itself. And the polarity of that voltage is opposite to the increase of the current. So you see where that phase relationship comes into play, where the voltage is opposite to the current. So with resistors, the voltage and the current were in phase with each other. Okay. And just as when you're increasing the current, you have an increasing magnetic field. When you decrease the current, you have a decrease in the magnetic field, and it will collapse. The magnetic field will collapse onto the inductor. And what that does is, when the magnetic field is collapsing, it will cut through the coil and it will induce a voltage across the device. So if you decrease the current, it will cause the magnetic field to collapse, and the collapsing magnetic field will be opposite the voltage of the collapsing magnetic field will be opposite to the current. Not the voltage of the collapsing field, the voltage induced in the device will be opposite. So here's a picture, and so we have a source which is right here. Okay, so all this time we were talking about DC sources, but this is the AC source. We have a switch and an inductor. So it kind of looks like a resistor, but it's actually, you see, it's like coils. Okay. And this is the magnetic field. So when the switch is closed, you have a current flow that will increase from 0 to the maximum current. So when you have that increase in the current, you will have this magnetic field being developed out like this. And what that does is it induces a voltage which will be opposite in the direction of the flow of current. So before it reaches its maximum, the voltage, it changes in the polarity in an AC signal. And therefore you will get a change in the current. So this causes a reverse voltage induced back into the coil. And this EMF is electromotive force. It's the same thing as voltage. And this developing and collapsing magnetic fields is a 90-degree lag. So here's a picture which shows you have the current that is increasing, and with that current increasing, you get the increasing of the voltage. And then you have a current that is decreasing, then you have a voltage that's decreasing. And in the phase relationship, how voltage and current works is that the voltage leads the current by 90 degrees. When you have inductors in series and parallel circuits, it's very similar to resistors in series and parallel circuits. So if they're in series, then you just add them up. It's very similar to the resistance circuit. And a parallel will be the same thing. This is that reciprocals of the reciprocals formula. Or you can use the product over sum formula. One of the most interesting devices with inductance is a transformer, and how that works is by the principle of mutual inductance. So what that means is, if you have a coil like this and another coil like that, then a magnetic field that's developed across this coil will have a corresponding magnetic field developed on this coil. And notice that these two are in parallel with each other. Which is this constant here? That it says that they are in parallel. Now in this case, it is perpendicular to each other. And you will have a lower, or you will have no voltage developed across this one, because actually this less flux lines cutting this device. Okay. Inductive reactance is the same thing, or well, very similar to what we already have talked about resistance, but it is dependent on the inductance. And inductors, they will oppose the current, and this is of course dependent upon frequency. Okay? And that's because of this lag that you get between the voltage and the current that's developed. So in this case, the opposite, so we just rearranged Ohm's law, right? Instead of I being voltage divided by resistance, so we just turn them around and put resistance up here and current goes down here. So in this case, the opposition will be 10 kilo ohms in this circuit, which means that this device will oppose the flow of current up to this number here. And remember that this happens only when we have a change in current. And here's the formulas for calculating the resistance. So X of L is the same thing as inductive reactance. It's like resistance. But because it is dependent on inductance and it is dependent on frequency, you say X of L. So this is the same thing as Ohm's law, right? Now the only different one is this formula, which says 2 pi FL. So 2, it's constant pi 3.14. The constant F is the frequency. This letter F is frequency, and L is the inductance value. L is the inductance, F is frequency, pi 2. So it's not the same thing as Ohm's law, obviously now. So we'll talk about how we calculate this. So we have a circuit like this, and we want to know, well, we know what the X of L is, right? So we want to know what is the current in this circuit. So we can use this formula. So current is equal to voltage divided by, well, we used to say resistance, but it is inductive reactance in this case. It's 1 kilo ohms, right? So it'll be 12 milliamps. We'll come back to this in just a second, and we'll build this circuit, but I want to continue on to something else for the time being. So this is talking about series and parallel reactances. One of the most important, well, I don't know about be most important, but at least a very important device using inductors is transformers. And if you remember, like the beginning part of the course, we were talking about AC versus DC, and transformers obviously not played the major role in that debate. So you need to have some way, you have a power plant, it produces power, and then it transmits over long distances to the consumer. So transformers is the device that will transmit the power from the power station to the consumer. And remember, we talked about Edison and Tesla and all of those, and how because of Tesla's idea of stepping up the voltage and stepping down the voltage, we were able to transmit power over long distances. And that happens only with AC. So at the transmission power plant, you have some kind of step-up mechanism, device, which is the transformer. And notice this transformer it's two inductors. There's something else that's interesting you should note is that you see the number of coils here, and you see the number of coils here. You have more coils on this side, on the right side, right? There's less coils on this side, there's more coils here, and that makes a step-up transformer. And then on the opposite side, you have more coils here and less coils here. So that makes it a step-down transformer. So we have two sets of transformers. Well, actually we have way more than that, going from a power station to a consumer. But the big picture of it is you have a step-up transformer at the power plant and you have a step-down transformer at the consumer end. And that's because we want to transmit power over long distances. So here's some examples of some voltages and currents. So one of the highest in the world is a 12 megavolt. So the M is 10 to the 6th power, right? Not 12, 1.2 megavolts in China. And most transmission lines are in the kV ranges. I think there's one coming, I don't know about Wisconsin, to Platteville, but in the Madison area there is one, I think a little bit higher than this. So the generation is 11 to 22 kilovolts, and then you have step-up transformers that step up the voltage. And remember, this is for that power loss concept, right? And then you have substations. If you go down, I think it's Southwest Road and 151, you will see one of the substations. which steps down the voltage. So it will step down the voltage. So let's say it was transmitting power at 138 kilovolts. It will step it down to 26 like this, and then it will step it down further when it comes to the consumer itself. So this is like that, the transformer that you see on a pole. So these are some transmission power plants in the state of Wisconsin. And it's actually, I don't know, well, it's a fact actually. Whether it's a good thing, bad thing, I'm not going to say that. But you notice that in 2016 at least, 51% of our power came from coal. And I'm not going to debate whether that's a good thing or bad thing. I think if you're working in a coal mine, you may have very strong opinions on that. Fortunately, over the years we have reduced our dependency on coal. So we, from 2016 to 2019, 51% to 36%. But even to this day, the majority of the power in the state of Wisconsin is coal power. Whether that is good or bad, I'm not going to say in a public forum. You can decide for yourself. But we are making strides. Whether natural gas is so much better, again, those are debatable issues. But we have increased our power generation in renewable power, which is I think is a good thing. I don't think anybody will debate that part. So one of the most important devices, well, whether it's most important, I'm not too sure, but anyway, it's a very important device, certainly in the transmission of power in AC, is a transformer. And the transformer is just two coils which are next to each other. And the transformer works on the principle of electromagnetic induction. So you have an AC input like this, and you go through a transformer, and then you have an AC output like this. Now in this case, the input and output voltages, the amplitudes are the same. So that's the maximum voltage you can see up there. They're the same. But so this is isolation transformer, but most transformers do something else to the voltage. For example, if you talk about, and I'm making a gross example here, but you know, if you talk about the phone charger, produces about 5 volts, but you plug it into the wall socket, which is 110 volts, right? Now there are a number of intermediate steps. For example, the input voltage is AC and the output voltage is DC, but the fact remains that there is, from 110 volts to about 5 volts or so. But it uses transformers. And you've seen these, right? So that's a classic example of a transformer. Not these. So here's a good example of a transformer. Have some terminals here, and then there's some wiring out here. I don't know if you can see any of the writing here, but they'll mark on the transformer what the turns ratio or the characteristics of the device. But just by looking at this, I can say that this must be the input part, and that's because I can see like a black color wire, which is live wire, white is neutral, and the green color, which is a ground wire, and this will be the output. There's another transformer. And you notice that it has, so these markings will also say which is input and output. And it will also say like what these voltages are. So it will say like input voltage is something and the output voltage is something. So here we have a transformer which has 110 volts input, and it has 12 volts, 0 volts, 12 volts. So that this 12 volts, 0, 12 is this part right here. So the total voltage, and actually you can see those arrows, right? So the total voltage in here, if you went from this blue color line to this blue color line, is 24 volts. But if you went from this blue color line to this black color line, it's 12 volts. And you notice that this is the input part. Notice both of these wires are the same color, because these have different colors. So transformers is two coils placed next to each other, and they have isolation. So another thing what this transformer does, it isolates the input from the output. So here's different kinds of transformers. This is an air core transformer. There is no core in here. This is an iron core transformer, ferrite core transformers. By putting this core in here, all it does is it increases the efficiency of the transformer. So here's the input voltage of the transformer, which is on this side right here, and this is the output. And this talks about the ratio of the input terminals. Okay. And there's no connection between the secondary and the primary. It's just an air gap with a metal core in the middle. Now in this case, you'll notice that the number of coils here is the same thing as the number of coils here, which corresponds to this voltage being the same voltage as this one. Notice that the input and output are not connected. So this part here is not connected to this part. There's an air gap between the two. So here we are talking about a step-down transformer. So you see the peak here and the peak here is less, right? So the secondary voltage is less than the primary voltage in this case. And you see the number of coils is less too. This has more coils, right, than this one. And just looking at this, you can tell that there is way more coils here than this one here. So this has, well, input voltage 100 volts. So the output voltage will depend on this ratio of these coils between the input and the output. So just looking at it, you could say it's a step-up transformer because there's more coils on the secondary. This is, so it's 5 turns and 20 turns. So this has 5 turns in here, there's 20 turns here. It looks more than 20, but anyway. So what that means is that the output voltage will be 4 times greater than the input voltage, right? Because it's the ratio 5:20. So if this is 100 volts, if it's 20 turns, then it'll be 400 volts out here. And obviously enough, the current is not going to be stepped up also, then, because if that is the case, then you will have increase of power. You can't have increase of power, right? So the output current is not going to be 10 amps. The input and output power will be essentially the same. There's usually some kind of loss in these things, but it's a very, very small loss. So here we talked about power before this, so it's 10 amps here, it's 2.5 amps here. So we have 100 volts input, 400 volts output. And the power is 1000 watts input and 1000 watts output. The power will not change between the input and the output. So here's for 3 different types of transformers. Step down transformer, which means you'll have less voltage on the output. Step up transformer, where you will have more voltage on the output. And isolation transformers, they have the same voltage as the input and output. A center tap transformer is like a middle. Remember that previous transformer where you saw where did we see that transformer? There, this one here. The 2 blue color and a black wire. So this is a center tap transformer. This is that center wire. And the output will be, the center tap means exactly 1/2 of the output, total voltage output here. When we talk about turns ratio, so in this case, in the primary, there is 320 turns, and just a second, point of it, bonkers. All right, there we go. So in this one, the primary has 320 turns, and the secondary has 80. You can see by just looking at this, right? There's more